Hey there, I'm Floppy. Today we will be looking at the generalized power reduction formula for cosine. The derivation will be mainly based on these two formulas. It is not a necessity to know them in order to follow the video, but I do recommend you to watch my other videos for greater understanding. With that said, let's put them on the side and jump into the derivation. The first thing we want to do is to express cosine in a way so we can handle the exponent. That is to use the complex identity for cosine. So cosine theta to the nth power is equals to e to the I theta plus e to the negative I theta divided by 2 to the nth power. For the right side, we will be factoring out the 1/2 factor. Now, we will be using a little substitution to make things more obvious. Namely, e to the I theta equals to a and e to the negative I theta equals to b. Using binomial theorem, we can plug in e to the I theta for a and e to the negative I theta for b, giving us the following sum. By exponential properties, we can move down the exponent k and n minus k. We can now get rid of some parentheses by distributing I theta, negative I theta, with n minus k. We can then combine the exponent and factoring the theta out. The left part is, as we know from earlier, a fraction of cosine theta to the nth power. Wait, now we got e to the power of I and something, which is a perfect situation for Euler's formula to shine. What we do is we plug in the exponent of e without the I into cosine and sine, which gives us the following sum. Now notice that the left part is a real function, which means that the right part must also be purely real. So this implies that I sine theta must be equals to 0, leaving the right part as a sum purely dependent on cosine. And this, my friend, is exactly the same formula I showed you in the beginning. Wait, this formula is way too complicated for me to remember. I have no idea how to use it. Alright, I guess I will dissect the formula and show some example. I promise you, you will know more how to use the formula in the end of the video. We can start by looking at the sum notation. It says that we are summing from 0 to n. If we try to count from 1 to n, then we would have n numbers. So if we add another number to the n numbers we already have, then we have n plus 1 numbers, hence n plus 1 terms to sum. And if n is even, then we know for sure that n plus 1 is odd. And conversely, if n is odd, then we got even numbers of terms to sum. Maybe that doesn't tell you much right now, but you will see why it matters later. We've been represented by binomial coefficient with this formula, but you could just use the Pascal's triangle to help you out. The binomial coefficient n choose k is really just a number located on the nth row and the kth place. But don't forget that the first row and the first place of the triangle starts with 0 and not 1. Now we can continue with the cosine part. I will demonstrate an example to show you how the 2k minus n radian factor works. If we let n equals 6, we will get these result as radian factors when we plug in different values of k from 0 to 6. But remember that cosine have a nice symmetry property, namely cosine of negative theta equals to cosine of theta. So cosine of negative 6 theta equals to cosine 6 theta, and cosine 4 theta is equal to cosine of negative 4 theta, and so on. This means that whenever we see a cosine, we multiply it by 2, since the sum will always include both positive and negative values of radian factors. The final result is that the sum will ultimately generate these terms. I have also included some coefficient, which is really just binomial coefficient. The last term, which in this example is C3, is without cosine, and the reason is after the previous term 2 times C2 cosine 2 theta, we then get cosine of 0 theta, which is just 1. Now let's take a look at some examples to really see how the formula works. The first example is a well-known cosine theta to the second power. The first step we're going to do is to write down the 1/2 to the nth power. Then we take 2 times the first binomial coefficient times cosine of whatever the n is, and then times theta. The next term is once again 2 times, but the second binomial coefficient times cosine, but the radian factor is decreased by 2. So all in all, this is equals to 1/2 cosine 2 theta plus 1, as expected. Now let's take a look at the cool example, cosine theta to the 6th power. We once again begin with writing down the coefficient 1/2 to the nth power. The first term is going to be 2 times the first binomial coefficient times cosine of n theta. The next term is going to be 2 times the second binomial coefficient times cosine of n minus 2 theta. And the third term is then 2 times the third binomial coefficient times cosine 2 theta. So lastly, we add the fourth binomial coefficient in front of cosine 0. But don't multiply by 2, because it only appears once, as you can see on the Pascal's triangle. We can simplify this to 1 over 32 times cosine 6 theta plus 6 cosine 4 theta plus 15 cosine 2 theta plus 10. We have seen cosine to some even power, but what if the power is odd? Well, it's actually super easy, since the odd power implies that there will be even numbers of terms to sum, as a conclusion from earlier. So how does this benefit us? Well, now when we have even numbers of terms, we get the nice symmetry property, since we don't have to worry about the binomial coefficient in front of the cosine 0. So we get the same factor in the beginning, the same factors of 2 in front of cosine, the same binomial coefficient but you start with an odd number, and the same radian factors, which also starts with an odd number and decreasing by 2 for every term you add. Now I encourage you to pause the video and try this on your own if you can figure out the power reduced form for cosine theta to the 5th power. Are you ready? So here is the answer. After simplifying, we get 1 over 16 times cosine to the 5 theta plus 5 cosine of 3 theta plus 10 cosine of theta, which is equals to cosine theta to the 5th power. Look, even Floppy is happy, and I hope you also enjoyed the video. See you next time.